Welcome to the Algebra 2 video on Unit 0, Section 1, Key Features of Functions. So what we want to be able to do, first of all, is identify if what we have is a function or not. Now to do that, let's talk about some foundational information. We want to kind of get some of the terminology under our belt. A set of ordered pairs, so we know what a set of ordered pairs looks like. We've got one right here in front of us, 3, 7. 3 is our x-coordinate, 7 is our y-coordinate. We can graph that point on a graph. If we have a set of these, so we have 2 or more of these, then we have a set of ordered pairs that forms a relation. Now the set of first members of the ordered pairs, or our x values, those make up our domain. And then the second members of our ordered pairs, or our y values, those together make up our range. Okay? So if we're talking about domain, we're talking about all the x values that are contained within our function. So we're going to be looking from left to right along the x-axis. If we're talking about range, we're talking about all the y values that are part of our function. So we're going to be looking from bottom to top along our y-axis. So if we have an ordered pair, this first number is our x-coordinate. This is our domain member. And the second coordinate, or our y-coordinate, that would be our range member. Now let's talk about functions. Now functions are made up sort of a special way, okay? You can't just say any graph that you have is a function. There's a very specific definition of what a function is. And what a function is a relation in which each element of the domain is paired with exactly one element of the range, okay? So we can only have one y value go to one x value, or I should say the other way around, one x value go to our y value, okay? So this is kind of how I like to look at it visually. We have an x value. That's our input, okay? This is the number that we're putting in. Then we put it into some function, and on the other side, we end up with a y value, okay? And that is our output. Okay, so you have some number for x, you put that into your function, you do the math, and out comes your y value, which is your output. So let's look at this visually. Let's map a set of numbers, okay? So we're going to do that by first drawing a couple of ovals or circles. Okay, here's one, and here's another one. And I'm going to put in some values, okay? We're going to put in maybe 1, 2, 3, and 4. And in the other one, let's put in 1, 9, 16, and 4. Okay? Now for this to be a function, we are going to pair up one value from our x's, which would be your left-hand circle, and we're going to pair it with one value from our y circle, or our right-hand circle. Okay, so let's put 1 to 1. Let's put 2 to 4. Let's have 3 go in and 9 come out. And then 4 will come in and 16 will come out. Okay, so now we have one number from our inputs, okay, or our domain, and that goes to a member of our range. And in between, we have a function that is getting us from one number to the other. Well, can you think of what type of function we would end up with this? Well, look at the relationship. We have one going in and one coming out. Okay, well that doesn't tell us a whole lot, but if we look at another item, maybe that we'll get some information out of that. So we have 2 go in and 4 come out. Okay, well we know 4 is 2 times 2. We know that it's 2 squared. which is 2 times 2. We know it's 2 plus 2. Well, let's look a little further. How about 3? 3 to 9. Well, 3 plus 3 is 6, so that's not our relationship. 3 times 3, or 3 squared, okay, that's 9. So I'm starting to see a relationship form here. We've got 1 squared, 2 squared, and then 3 squared is 9. How about 4 squared? Oh, that gives us 16. So our function turns out to be x squared. We took a member out of our domain. That was our input. We put it in place of x, and when you square that member of the domain, you get our value for our range. That's how functions work. Now let's talk about identifying a function. So if we want to identify a function, we may be given a set of ordered pairs, and you see that here in the bottom of the page. We'll get to this example in a moment, but let's talk about the different types of possibilities we could get out of our set of ordered pairs. Well, first of all, let's look at the domain member. That's our x values. Are any of the x values or our domain members the same? If none of them are the same, so all of our x values are different, then you can stop right there and you can determine that we have a function. All right, well, say you look at 2 or more members of your domain or your x values, and you have 2 or more that are the same. Well, then we have to ask our next question. We've got to look at the range values that go with those domain values that are the same. Okay? Are any values for the range different? Okay? If they are not different, then we have a function. And that would make sense, right? Because if we have x values that look like each other, and for those x values, they both have the same y value, then we just have the same point repeated in the list, right? It's the same point. So therefore, if the point is listed twice, it's just listed twice. It's just there twice. So we still have a function. However, if we have the same x values, but they have different values, then we do not have different values for the y, then we do not have a function. Okay? So in this case, it would be not a function. Okay, so let's do some examples. All right, this flowchart just kind of gives you an idea of the questions you ask to determine if it's a function or not. But the best way to understand this is to look at some examples. This kind of locks in the knowledge for you. So let's look at example 2. Okay, this is your set, and I've gone ahead and listed all those values down here once again so we can work with them. Well, first let's look at all the values for the domain. Okay, well, since all of these values are different all the way across, these are all different inputs or different x values, then therefore we have a function. And we can stop right there. So this was the easiest situation in which to determine if a set of ordered pairs is a function or not. If all your x's are different, you have a function. You don't even have to look at the y's. Okay, now let's take a look at another example. Here's example 3. Okay, we've got another list of ordered pairs. Let's take a look at the x values. And in these x values, we have -10, -5, 2, 0, and 2. Okay, well, right here we have found that 2 of these are the same. So we have the same input. Same input for these 2 sets of ordered pairs. So now we're going to look at the y values that go with these 2. So for the first one we have 4, and for the second one we have 5. So here we have different outputs. Okay? Since the output is different, then we do not have a function. Okay? So this is the key here. If you have the same input for x's, but you have different values for y's with those x's that are the same, then we do not have a function. Let's look at this next example. You have -4, -2, 0, 0, and 2 for your x's. All right, well, once again, we have two x values that are the same. And it doesn't have to be 2. It could be 3, 4, even 5, even more than that. But for simplicity, let's just say this example, we have 2, okay? Now let's look at the y values that go along with the same x values. Well, both of these are -4. So we have the same output. Since we have the same output, we have a function, because we're essentially just repeating the same point twice. So that is how to find a set of ordered pairs, or find within a set of ordered pairs whether or not we have a function. Now, to determine if we have a function when looking at a graph, I feel like this is an even easier task, because we have a test that we can run, and it's called the vertical line test. Now, in a vertical line test, if any vertical line drawn on the graph of a relation passes through no more than one point of the graph, then the relation is a function. And we've got a few examples to show you how this works. So let's take a look at this first example. If I were to draw a vertical line, okay, well, I'm just going to draw a line right here, up and down. And if I were to take this line and drag it across the graph, starting from left to right, okay, well, we haven't gotten to the function yet. We don't get to the function until we get about here. Okay, so we're going to start from the left-hand side of the function, and we're going to drag this line across the graph. And all the time that we're doing this, the graph of the function only crosses this vertical line one time, never more than once. So since it doesn't cross that vertical line any more than once, then we can therefore say that this graph is a function. Okay, let's look at the second example. We have our vertical line here. We're going to do the same test. So we start from the left-hand side of the function, and then as soon as we get this line moving right, we're already crossing the function more than once throughout pretty much the entire graph except for right where we start. You can see that we are crossing this line here and here. Okay, so since we have more than one crossing of the line of our equation, then we can say it's not a function. And it's not a function because it does not pass the vertical line test. Let's look at a couple of more examples so we can get comfortable with this. Okay, so we are going to draw our line once again, vertically up and down. And now we are going to drag this line across. Now, if you're doing this on a sheet of paper, you may want to do this using a pencil if you want to use something to see if it passes the test. So here we have this circle that's plotted on this graph. And if we draw this vertical line and drag it across, well, you can see that it's crossing this line more than once, right? We have it crossing here, and we have it crossing here. So since it crosses this vertical line in more than one place, then we can therefore say that this is not a function. So we'll go ahead and write that down here. That is not a function, Again, because it fails the vertical line test. Okay, let's drag this vertical line across this graph. Well, everywhere across this graph from left to right, as we drag a vertical line across, this graph does not cross the vertical line more than once the entire way. So, since it doesn't cross more than once the entire way, we have a function. Now that we know how to identify a function, let's talk about some features of a function. So the first key features I want to bring up are your x-intercept. So we'll write that in here, x-intercept. And your x-intercept is the value of x when the value of the function is y is 0. So when you have y equaling 0, your value of x is an x-intercept because you are along the x-axis. The x-intercept also has two different ways that it can be called. You may find it encounter it being called a root or a 0. So if you come across a problem where it asks for the roots of a function, it's asking for the x-intercepts. Same thing with 0. If it's asking for what the zeros of the function are, it's asking for the x-intercept. Just like we have an x-intercept, you also have a y-intercept. And that is the value of the function when x is 0. So we're going to be along the y-axis for your y-intercept. Now let's talk about where we'll find that on this graph. So we're going to go ahead and come on down to this graph, and we're going to use this graph for the next couple of concepts. So we just talked about x-intercepts and y-intercepts. Well, this graph has 3 x-intercepts. There's one here, and there is one here. Okay, so right here, and right here. Those 3 spots would be your x-intercepts. So we have an x-intercept here, and you have x-intercepts here. This graph also has a y-intercept, and that can be found along the y-axis right here. So let's go ahead and put a little arrow on that, and let's label it as our y-intercept. Okay, now let's talk about the next concept, and that would be positive and negative intervals. So your positive intervals are the sections of the function in which y is positive. So that would be your positive intervals. In fact, let me use a different color that's going to go along with what we're going to be using on the graph. So we've got your positive intervals. Okay, so basically we're looking at all the values that are above the x-axis. Sections of the function in which y are negative are your negative intervals. And these are parts of your function that are below the x-axis. Okay, so here we are. Let's start on the left-hand side of our function. Okay, now let's go from left to right along the function. Well, we're below the x-axis, so we're starting negative. And as we travel along, once we get to this x-intercept here, we get to where we are no longer negative and we start going positive. In fact, let me see if I can draw this line a little bit neater. So we're going to use a dashed line, and we're going to make it green. Okay, So basically along up until you get to this dashed line, from the left on over, this would be where you have a negative interval. Okay, so this first interval is negative. Well, then we're above the x-axis. So we have positive y values, so therefore we have a positive interval. And this positive interval goes until we get to our next x-intercept. So it goes to about, it goes to about here. Okay? Well, then we're negative again. Okay? And we cross the y-intercept, and we get to our next x-intercept, in which we become positive again. Now, it's important to note that just because we get to an intercept along the x-axis, an x-intercept, that doesn't necessarily mean that we are going to go from negative to positive or negative. Because there could be a case where we actually start off negative, touch the axis, and then go back down to being negative again. In which case, we go from a negative interval to another negative interval. So here we are. This is a negative interval. And then here we have a positive interval to finish out. All right, now let's talk about maximum and minimum values. Okay, so the highest point on the graph of a function is its maximum. The lowest point on the graph of a function is its minimum. Now, there are two types of maximums and two types of minimums, okay? But these are your generic definitions for what maximum and minimum are. Okay, so we have our maximum and we have minimum. Over here on the side, I'm going to make a note of the two different types of maximums and minimums. Okay, the first type is absolute. Okay, so if you have an absolute maximum or minimum, then that means it is the largest value or the smallest value in terms of y. It's our highest or smallest y value in the entire graph. There's nothing else that is larger in the case of a maximum or smaller in the case of a minimum. So for example, let's take a look at this graph. We have a minimum on this graph, okay? And it's right here at the y-intercept, okay? So that is not only our y-intercept, but it's also our minimum. So right here, we have a minimum. Okay? But it's also an absolute minimum because everything else on this function is happening above this point. So this would be an absolute minimum. All right? So absolute refers to the entire graph. Well, let's talk about absolute maximum for this graph. Well, this graph goes up, and then it comes back down to the absolute minimum, and then goes up, and it continues forever. That's what this arrow on the right-hand side indicates, that this graph continues indefinitely. When this is the case, then we're going to infinity, but we can't actually put a value on infinity. So we would say that there is no absolute maximum in this case. So no absolute maximum. Okay? Now, let's talk about the other type of maximum and minimum, and that would be relative maxes and mins. And when we're talking about relative, we're talking about the neighborhood. Okay? So let's say that we have a neighborhood right here. Okay, and we have an absolute minimum in this neighborhood. But we also have a peak here, right, along this positive interval. We have a peak, and we can call this peak a relative maximum because it refers to the neighborhood in which this peak resides. Okay, so far we have covered x-intercepts and y-intercepts, positive and negative intervals, and maximum and minimum values. Now we're going to go to the next page, and we're going to talk about increasing and decreasing intervals. And we're going to start fresh with this graph, okay? So let's take a look at what increasing and decreasing intervals are talking about. So sections of the function in which x and y are both increasing are called your increasing intervals. Increasing intervals. Okay? Sections of the function in which y decreases as x increases are your decreasing intervals. And I know this sounds a little wordy, but all we're saying is where the graph goes up, we're increasing. Where the graph goes down, we're decreasing. Where the graph goes up again, we're increasing. Okay, so it's fairly simple to pick out when we're looking at it on a graph. Okay, so let's go ahead and let's plot where things are. So we're increasing from the left-hand side of this graph up until around here, which is about where our relative maximum was, right? Then we're decreasing until we get to the y-axis. And along the y-axis is where we change back to increasing again. So this is where our intervals would be for increasing and decreasing. We start with an increasing interval. Then we go to a decreasing interval. And then we go back to an increasing interval, which continues forever. Now, we talked about it a little bit, and this is what's happening when we have an arrow on the end. This gets us into end behavior, okay? So the ends of a function do one of two things. They're either definite, which means they terminate, or they're indefinite, meaning that they continue forever. So continuing forever is indicated by an arrow, and a definite end is indicated by either a solid or open dot. Okay? And we need to know how end behavior works because that pulls us right into domain and range. Okay? So the domain and range, we talked about this toward the beginning of this video. It's the set of all x values. That's our domain. And the range is our set of all y values. And we can actually look at both our end behavior and our domain and range on this next graph. Now this is the same graph that we were using for the last two pieces, okay? So here's our indefinite. In fact, let me draw this with this, just so it's a little clearer. So here is our indefinite end on this side. And when we say indefinite, we mean that it continues forever. And then on this end, we have a definite end. And that means that it terminates. Okay? So this is our definite end. And it terminates. All right, well, now let's talk about our domain and range. Now we know where the ends of our function are. We can determine what our domain and range intervals are. Okay, so for domain, we're going to be looking along the x-axis. So we're looking from left to right, okay? So let's put this in red. So we're going to start from the left-hand side of this graph. And this is as far left as the graph goes, okay? So when we start from here, our domain starts here, okay? So this is our domain. And our domain is going to continue on to the right. And it's going to continue on forever because on the right-hand side of our graph, of our function, we have an arrow, meaning that it continues forever. Now, let's look at the range. We can look at the range in a similar manner by looking at the bottommost part of the graph first. And when we look at what our bottommost part of the graph is, it's at that absolute minimum value. Remember the absolute minimum, there's nothing that goes below that. So our range would start here, because when we look at range, we go from bottom to top. Okay? So our range begins at that minimum value. And our range is going to continue on forever as we go up. So we're going to go from bottom to top, and our range will continue forever because this arrow indicates that it continues on forever, going up and going to the right. So therefore our domain, again, our x values, we're looking along the x-axis, starts from this left-hand side and continues to the right forever. Our range along the y-axis, looking from bottom to top, begins at our absolute minimum, and it continues on forever going upward. That's how you find domain and range. Now there are two ways that we can notate domain and range. The first way we can notate it, and in many cases, the most common way that you see it notated, is an interval notation. And in interval notation, we use parentheses and brackets on either side of our bounds, okay? So our smallest value for our domain would be on the left-hand side, or our range, the smallest value would be on the left-hand side. Our largest value would be on the right-hand side. Now, if we are not including our bound, which means we either have an open dot or we have an arrow, meaning it's going to infinity, because we can't include infinity because it's not an actual number. We use a parentheses. Now, if we have a solid dot on the end of our function, then we use a bracket, meaning that we do include that value. Okay? So, again, parentheses means that it's open, and it means that the value is not included. Then on the other end, we have closed, which is indicated by a bracket, meaning that it is included. So that is interval notation. Now let's go on to the other form of notation, which is perfectly acceptable to use. It's just another way of writing the same thing, and that is set notation. And in set notation, we are going to use inequalities. So we'll use a greater than or equal, a greater than or less than sign, or a greater than and equal to or less than or equal to sign. If it is open, again, when we're talking about open, we're saying that it's not included, which is going to be the case if we're going to infinity, or if we have an open dot, we will use a greater than or less than sign. If it's closed, which is indicated by a solid dot on the graph, and a greater than or equal to or less than or equal to sign, then we are saying that it is included. All right, now that we've talked about what all the key features of functions are on a graph, let's talk about how we actually notate it in a real problem sense. So let's do a couple of examples. So let's start off with example 9 here. Okay? So in example 9, we have a simple graph. On both ends, it terminates, and we're including what's on the ends. Okay? Just a quick overview of what we're looking at. Well, let's first find our x-intercepts. So we're going to look along the x-axis and see where this graph either touches or crosses the x-axis. And we have one spot here at x equals -2. Well, we can notate this as an ordered pair, -2, 0. We also have a y-intercept, and we go along the y-axis to find that. It's at y equals 3, so we can indicate that in an ordered pair as well as the point 0, 3. These are specific locations for those intercepts. Now let's talk about domain and range. Remember, domain is all of the x values, okay? So we're looking from left to right, and we're looking at what all of our x values are. So we start here on the left-hand side, and our first x value is -4. So I'm going to go ahead and write -4 over here. Then I go over to the right-hand side, and our ending x value, if we go to the right here and we follow it on down to the x-axis, is 2. Okay? Now our last question for our domain is, do we include or not include our endpoints? Well, we have a solid dot on the left-hand side, so that means the -4 will be included, so we're going to use a bracket. On the right-hand side, we have a solid dot, so the 2 would also be included. And that would be our domain. This is an interval notation. We can also write it in set notation. We start with our left-hand side, and then we go to our right-hand side, which is 2. We stick x in between, and since we are not, or I should say since we are including it, then we'll do a less than or equal to sign in between the -4 and x, and a less than or equal to sign between the x and 2. So essentially we're saying is x is all values between -4 and 2, including those end points. Now let's talk about the range. The range is found very much like the domain, except now instead of looking along the x-axis, we're going to look along the y-axis. And just a side note here, the range is the only piece of information that we're going to be looking at where you use y values instead of x values. So when we talk about other interval types, such as positive and negative intervals and increasing and decreasing intervals, those will be in terms of x, like our domain. Range is the only thing that is going to be terms of y. So let's look at the range. We're starting here at the bottom of our graph. We follow this over to the y-axis, and we find that our value for y is -3. So that is going to be our bottom end. Then we go on up. The top part of our function goes to 6, and that is the other side of our range. And just like with the domain, we have closed dots on both ends, so it's closed, and we use brackets. Range can also be indicated in set notation, and we do that very similarly by putting -3 on one end and by putting 6 on the other. But this time, since we're going along the y-axis, we're going to put y in between, and since we're including our bounds, we'll use less than or equal to in between each of these. Okay, now let's talk about our maximum. Our maximum value on this graph, since it terminates on both ends and it is only going up, is very simple. We have a value for our maximum, and we can set it in an ordered pair. So our maximum value is the top part of the graph, and we have x2, and we go up to y, which is 6. So our maximum is at the point 2, 6. Minimum can be found similarly. This is the bottom part of our graph. So we go down to y equals negative 3, x equals negative 4. So over to negative 4, down to negative 3. Those are our coordinates, negative 4, negative 3. Now let's talk about the positive intervals. The positive intervals occur where we have the graph above the x-axis, where y is positive, okay? So our graph begins negative, and then we go on up until we get to negative 2. Once we get to x equals negative 2, then it becomes positive, and it stays positive until the graph terminates at 2. So our positive interval goes from negative 2 to 2. Now here's the question. Do we include our bounds? Well, on this end, we have a dot, which means where we terminate, we do include it. And that makes sense because at the value x equals 2, our y value is 6, and that is certainly positive, so we do include it. How about at negative 2? Well, at negative 2, we're crossing the x-axis. So what is our value at x equals negative 2 for y? Well, since we're along the x-axis, y is 0. Well, 0 is neither negative or positive. So therefore, we're going to use a parentheses and not include it. Again, negative 2, when x is negative 2, y is 0. Since 0 is not negative and 0 is not positive, we do not include it as part of the interval. If we were to write this in set notation, we would use a less than with no equals sign on it. But since we are including 2, we will put the equal sign on that one. Finally, for negative intervals, well, it is the rest of the graph, right? So from negative 4 to negative 2, we have a negative interval. We include the negative 4 because there is a negative value attached to negative 4, but we do not include the negative 2 again because that value would be 0 for your y value. And this can be also put in set notation. Negative 4 is less than or equal to x, which is less than negative 2. So that is example 9. Now let's take a look at example 10. Okay? So now we have a little bit more complicated graph, but we still find all the information in the same manner. So let's start with our x-intercepts. Well, we have one point where we are touching the x-axis, and that is at x equals negative 2. So we can write that as the point negative 2, 0. We have one y-intercept where we're crossing the y-axis at y equals negative 1. So that would be at 0, negative 1. Our domain is all of our x values. Okay, so we're going from left to right, and we're doing all of our x values. So our leftmost part of the function is at x equals negative 7, and we are not including the negative 7 since we have an open dot. Then we go on through, continue right until we get to the end of the function in the x-axis, and that is at x equals 6. Since we have a solid dot, it's closed, and we include it with a bracket. Now, let's talk about the range. We're going along the y-axis, and we're going from bottom to top. So the lowest in the y that this function goes is along y equals negative 9, because this is the bottommost part of our function. Now we do include it because the graph actually touches negative 9. Okay? This comes on down to negative 9, it touches it and goes on up. Kind of like how here we're touching the x-axis, which coincidentally is actually the top part of our function in the y. So that would be the other end of our range. So our range is negative 9 to 0, and we include both ends. Now let's talk about the maximum. The maximum occurs at the top part of the function. Well, we just showed where that was when we did our range. So our maximum is at the point negative 2, 0. Our minimum is at the bottom part of the function, which we just showed. So this function happens to have an absolute maximum and an absolute minimum. For the purposes of my class, if it is asking for an maximum or minimum, but it does not specify which one, always assume absolute. And since this one has an absolute maximum and an absolute minimum, we can actually put values for both of those. And finally, let's talk about increasing and decreasing intervals. Very much like positive and negative, they kind of go hand in hand. So I'm going to show you a strategy so that you don't forget any piece of either answer. And the strategy involves starting on the left-hand side of the graph. Okay, well, we are decreasing first, correct? So we start from -7 and we're decreasing until we get to x equals -5. Okay? So that's going to be our first decreasing interval, -7 to -5. Now, once we get to -5, are we going to include that? Well, the answer to that is no, because we're going from decreasing to increasing. And when we're going from decreasing to increasing, in that moment, right in between, we are neither decreasing or increasing. We're essentially flat. So since that is the case, we are not including it. All right, so that's our first part of our decreasing interval. Now it's going to start increasing. So we're going to come up here and we're going to start our increasing interval where we left off with our decreasing interval, and that's at -5. Now we're going to follow this graph up. We're increasing until we get to -2. And -2 would be our bound on the other end of our increasing interval. Then as we get to -2, we start decreasing through the end of the function at 6. Okay, so now our other interval is -2 to 6, and we have managed to get all of our intervals without leaving anything out by doing both together. There's one last little piece I want you to put on this decreasing interval. Since we have two of them, we're going to join these two intervals with a little u in between. And that u stands for union. Okay, a couple more examples on identifying these features before we move on. So example 11. Let's take a look at the x-intercepts. Well, we've got 3 of them. One here, and one here. So our x-intercepts are going to be listed sort of like a list. We're going to have 3 sets of ordered pairs, -2, 0, 0, 0, and at 3, 0. Our y-intercepts, well, we've got one of them, and it happens to be the same place where we have an x-intercept, and that is at the origin, 0, 0. In fact, the origin is the only place where you can have both an x and y-intercept in the same place. Now let's talk about the domain. Well, here's a look at our ends here, right? We've got ends that are indefinite. They don't terminate. They go on forever. So this is how we handle the domain. Since we have an arrow on the left-hand side, then we're going in the negative direction on the x. Since we have an arrow on the right-hand side, this means we're going in the positive direction on the x. And in both cases, we're going infinitely in both directions. So our domain is going to be -infinity to infinity. If you were to write this in set notation, it's even easier to write. We write it as a fancy R that's got 2 bars on the left-hand side. In text, you would see it as a bold R, but since we can't really write in bold, we use this type of notation to represent R, or all real numbers. The range is similarly going to be going from -infinity to infinity because we are going down in the infinite direction and we're going up in the infinite direction. So our range is also negative infinity to infinity, and if you wanted to write it in interval notation, you would write it with the R representing all real numbers. Now, for positive intervals and negative intervals, let's do these hand in hand, okay? So we start on this left-hand side of the graph and we're negative, okay? So from negative infinity, we are negative. And we are negative up until we get to negative 2, okay? So when we talk about negative infinity, we're talking about it along the x-axis here. So our positive, or I should say our negative interval, we're starting from negative infinity and we're going to negative 2. When we get to negative 2, it becomes positive. And it stays positive until we get to 0. So we're going to write our first positive interval as negative 2 to 0. Then when we get to 0, we're negative again until we get to 3. So we're going to union this, 0 to 3. And then finally from 3 on to infinity is our final positive interval. And now let's talk about end behavior, okay? End behavior is what's happening with the ends as we go to negative and positive infinity, okay? So on this left-hand side, we have as x approaches negative infinity, because we're going to the left. And on this side, we have as x goes to positive infinity, because we're going to the right. So you're going to have two statements. So the first of which will be as x goes to infinity. And the second one will start as x goes to negative infinity. We want to see what the function does, or in other words, what does our y do, okay? So as x goes to infinity, that's on this side, on the right-hand side. Where's y going? Well, since we're going up, y is going to infinity as well. And we're going to write that as f of x. F of x goes to infinity. Now, on the left-hand side, as x goes to negative infinity, that's here on the left. Well, y is going down, which means y is going to negative infinity. So f of x is going to negative infinity. And that's how you write down the end behavior. As x goes to infinity, f of x goes to infinity. As x goes to negative infinity, f of x goes to negative infinity. And that completes this example. Now let's go on down to one more example before we move on to a couple of other topics to wrap up this section. So, example number 12, we're asking for the domain and range at the beginning. Well, let's start on the left. We're coming from negative infinity from the x direction, and we're going to infinity in the x direction because we're going infinitely to the right. So our domain again is negative infinity to positive infinity, or all real numbers. Our range, well, if we go all the way to the bottom part of our graph, it's coming from negative infinity on the right-hand side, and it's going to infinity over here on the left, because here we're talking about the y-axis, remember, when we're talking about range. So it goes down infinitely and it goes up infinitely, which means the range covers all real numbers as well. So we're going from negative infinity to positive infinity here too, which again is all real numbers. And you don't have to write both. You can write just your R symbol or just negative infinity to positive infinity. I'm just showing you two ways to write the same thing. All right, let's talk about maximum and minimum. Well, it infinitely goes up and it infinitely goes down. And if we're assuming we're talking about absolute, in both cases, we have none. But if you were to be asked for relative maxes and mins, well, our relative maximum, well, we have a neighborhood here. Our relative maximum would be 0, 0. Our relative minimum would be down here, right, where the graph bottoms out in this neighborhood. And that one would be -4, -8. And that's a relative as well. Okay, now let's talk about increasing intervals and decreasing intervals. Again, these go hand in hand, so it's a good strategy to just start from the left-hand side of the graph, see what's happening, and follow it all the way to the right. So let's start at the left. Well, we're decreasing to begin out with, coming from negative infinity, because remember, we're talking about the x values again. Remember, range is the only time we're using y values. X values are used for all other intervals. So, since we're coming infinitely from the left, we're going to follow the graph. We're decreasing up until we get to negative 4. So our first decreasing interval would be negative infinity to negative 4. Then we pick up from negative 4. We're increasing until we get to the origin, or 0, 0. So our increasing interval would be from negative 4 to 0. And then finally, from 0 on to positive infinity, because we go infinitely to the right, we are decreasing again. And that concludes our increasing and decreasing intervals. Now, let's take a look at end behavior. Remember, we're going to look as x goes to infinity, and we're going to also look as x goes to negative infinity. What is happening? So, for infinity, we're looking at the right-hand side of the graph. Well, is the graph going up or down in the y? It's going down. So, therefore, f of x goes to negative infinity. How about on the right-hand side? Well, as x, or I should say left-hand side, as x goes to negative infinity, because we're on the left-hand side, we're going up. So therefore, f of x goes to infinity. So this should conclude a look at how to identify features of a function by looking at the graph. Now let's switch gears a little bit, and let's talk about average rate of change. Well, the average rate of change is how fast the y values are changing as compared to the x values. Now, you may want to remember back to linear functions. The average rate of change is often called the slope because we used rise over run. Rise was our y values, and the run was our x values because we were going up and down with the rise and to the left and right with our run. Well, average rate of change works very similarly. We're given 2 points, and given those 2 points, we can figure out what the average rate of change is. Okay? So, we're going to talk about what the formula is for the average rate of change. And I'm going to give it to you in a couple different formats. So the average rate of change is your change in y over your change in x. Well, we have a mathematical way of notating that. We can notate it as delta y. So this is the Greek letter delta, delta y over delta x. Delta essentially looks like a triangle. This delta symbol, even though it looks fancy, all it is an abbreviation for the phrase change in. So whenever you see delta y, delta x, this just means change in y, change in x. And we can find out what that change is by doing y2 minus y1 over x2 minus x1. Now that we have a formula, let's do a couple of examples of doing average rate of change. So in example 13, find the average rate of change on the interval 1 to 4. Okay, and we're given a graph that goes along with the function that is being questioned about. So the first thing we want to do is find out what our x1, y1 is, and what our x2, y2 is. Well, Here on the interval, we are given what our x values are. Because remember, when we're talking about intervals, unless we're talking about range, these are going to be x values. So our first x value is 1, and our second x value is 4. Now all we have to do is find what our y values are that go with those x values. So we're going to come over here to the graph, and we are going to find x equals 1, which is right here along the x-axis. Now we're going to follow x equals 1 all the way up until we get to where the function is. And that function is right here at y equals 6. So for x equals 1, y equals 6. We'll do the same thing to find our other value. So we go to x equals 4. We follow that one down to the graph of the function. And that y value, if we follow it back to the y-axis, is -3. Now we have all the information we need to be able to calculate the average rate of change. So we have delta y over delta x, which again just means y2 minus y1 over x2 minus x1. And when we do this, we're just going to plug things in. So y2 is -3, y1 is 6, x2 is 4, and x1 is 1. So -3 minus 6 is -9. 4 minus 1 is 3. And so our average rate of the change is -3. Now, the question may come up, would it matter if we swapped these two ordered pairs and made 4, -3 are 1s and 1, 6 are 2s? Well, let's find out real quick. Okay? So let's say x1, y1 was 4, -3. And let's say x2, y2 is 1, 6. Well, let's plug this into our formula. Okay, so you have change in y over change in x, and this is y2 minus y1 over x2 minus x1. y2 in this case is 6. y1 is -3, so we're doing minus a -3. x2 is 1, and x1 is 4. 6 minus -3, well, we've got negative, so that's a positive, so 6 plus 3 is 9. 1 minus 4 is -3, and we still end up with -3. So no, it does not matter which order you have it in. The key here is you need to make sure that your 2's go together and that your 1's go together properly. In other words, that you're actually using the correct points that are actually along this graph. Okay? Let's do one other example. We're going to use a table of values to find the average rate of change. And for this one, we're going to find it on the interval -1 to 2. Well, this is even easier than doing a graph because the values are just given to you. So we need to know what x1, y1 is, and we need to know what x2, y2 is. Well, our x's again are given to us in the interval. So let's make x1 -1 and x2 2. Well, here's our table of values. Well, with -1, we just find the y value that goes with it, so it's -6. And for 2, the value that goes with that one is +6. And now we just go to the formula. Our change in y over change in x is notated as y2 minus y1 over x2 minus x1. y2 is 6. y1 is -6, so we've got minus a -6 over x2 is 2, and x1 is -1, so we have a minus -1. And when we do the math, we have 6 minus -6, which is 6 plus 6, which would be 12. And 2 minus a -1, which is 2 plus 1, is 3. So our average rate of change is 4. And this concludes the average rate of change section of the notes. Now let's move on to talking about constant versus linear functions. So, linear functions are what we want to talk about first. Linear functions yield a constant rate of change, okay? So therefore, in other words, the slope is constant. So, let's see what a linear function looks like in an equation, table, and graph. Well, in an equation, the key feature that you're looking for is that it can be characterized by an equation that can be written in the form f of x equals mx plus b, where m is your slope and b is your y-intercept. If it can be written in this form, then you have a linear equation. This form, and we'll be talking about this here in a moment, is called slope-intercept form because this is the form that gives you your slope and your y-intercept. For a table, we have to look at how fast our x's are changing and how fast our y's are changing and how it changes over time, okay? That sounds complicated, but it's a fairly straightforward process as to how we do this. So we want to look at what the difference is between these two values, and these two values for x. So between 4 and 0, we're changing by 4 units. Between 0 and -1, we change by 1 unit. And between -1 and -3, we're changing by 2 units. Now let's go over to the y's and do the same thing. Between 7 and -1, we go down 8 units. Between -1 and -3, we go down 2 units. And between -3 and -7, we go down 4 units. What we found here on the left-hand side, these are our change in x values. What we found on the right-hand side is our change in y values. So we're going back to what we previously talked about with average rate of change. We're going to find out what our change in y and change in x look like along the way. Well, our change in y value, starting at the top here, is 4, and the change in x value that goes with it is 2. Our change in x, or our change in y for the second set is 2, and our change in x is 1. So we're going to notate that as 2 over 1. And our last one is change in y is 8, change in x is 4. So we're going to notate that as 8 over 4. Okay, so now we have 4 over 2, 2 over 1, and 8 over 4. Well, 4 over 2, or 4 divided by 2, is 2. 2 divided by 1 is 2, and 8 divided by 4 is 2. So all of these equal 2. And since we all have the same value for all of these, then we have a linear function. So it's characterized by a constant value for m. So here we have a constant value for m, which is our slope. In fact, let me write constant value for m. Okay? So now, here's a graph. This is the easiest one to pick out. What you're essentially looking for is a line. But not just any line. You need to have a line that is not horizontal or vertical. So this is how you find a linear function, by equation, table, and graph. Okay? Before we move on to constant functions, I do want to give you the formula for lines and how you're going to see it, the two most often ways you will see a equation for lines. So this first one, this is your standard form of a linear equation. Okay, so your standard form of a linear equation is ax plus by equals c, where a, b, and c are real numbers, and a and b are both not zero. Okay. Your other form is your slope-intercept form of a linear equation. So here we have the slope-intercept form of a linear equation. And it is the form that we've been talking about already, y equals mx plus b, where m is your slope and b is your y-intercept. So now that we have those forms of our linear equations and we've talked about linear equations, let's talk about a constant function, okay? And this is what a constant function is. Constant functions are linear functions that yield a constant y for every x. Okay? It's actually fairly simple. In an equation, you're looking for a function that is set equal to a number. So here we have f of x equals 5 or y equals 5. It's just set to a number. It doesn't have to be 5. It can be 4. It can be 3. It can be 9. It can be 52. It can be 564,281. Just any number. In a table, it's just as easy to find if you have a constant function. It's characterized by a constant value for y. So in this table, you can see that every value for y all the way down is 5. Again, it doesn't have to be 5. It just needs to be the same number all the way down. And finally, for a graph, you have a line, but this time it is a horizontal line. Okay? So this is why a horizontal line is not considered a linear function, because it's considered a constant function instead. All right, let's do one final example in this section. All right, in this example, we're going to write an equation for the graph of the given function and identify the key features. So this is a catch-all, a little bit of a review of what we've done in this section to close things off. So let's start off by taking a look at the slope. So you may remember when we are looking at the slope for a linear function, we are looking at rise over run. Well, this line is slanted downward, which means it's decreasing. So you may remember when we have a decreasing function, the slope should be negative. When we have an increasing function, our slope should be positive. So let's start here at the y-intercept, which is 2, 0. In fact, let's go ahead and notate that that is our y-intercept. B equals 2. And let's see if we can find what the slope is. Well, rise over run. So instead of rising, we're going down. So that's our -1. And then we're running 1, 2, 3 before we get to where it crosses a grid again. So this means our slope is -1/3. In fact, I'm going to write it as m equals -1/3. Well, we have our slope and we have our y-intercept. That's all you need to write the equation of the line. So our equation is going to be y equals mx plus b, so m is -1/3, x plus 2. Okay, so now that we have the equation, let's just finish off by finding all the rest of the requested information. So x-intercepts, we go along the x-axis. There's our x-intercept, 6, 0. We already found our y-intercept, and that was 0, 2. Domain, well, we got an arrow on the left, an arrow on the right, so our domain is -infinity to +infinity. Our range, well, we got an arrow going down, an arrow going up. So our range is negative infinity to positive infinity. Our increasing and decreasing intervals, let's do these hand in hand. Well, this is fairly simple. It's decreasing the whole time, right? So since it's decreasing, it's not increasing anywhere. So there are no increasing intervals, and we're decreasing throughout all x values. Now let's do positive and negative. Well, we're starting positive from negative infinity, and we're positive until we get to x equals 6. So negative infinity to 6. And remember, we're not including 6 because at 6, the value is 0 in the y-axis or the y direction. And 0 is not positive, so therefore it's not included. It's also not negative, so we're not going to include it on the negative interval, and it goes on to infinity on the negative side of the axis. And then finally, last but not least, let's talk about the end behavior. So we're going to see what happens as x goes to infinity, and what happens as x goes to negative infinity. Well, on the right-hand side, as x goes to infinity, the arrow is going downward in the y direction, which means f of x is going to negative infinity. And then on the left-hand side, as x goes to negative infinity, since we're going left, is pointing in the upward direction, so therefore f of x is going to infinity, or positive infinity. So this is going to conclude section 1 of Unit 0. And our next section is going to be on linear function transformations and systems, and that is section 2, and you can find that information in the next video.